Thursday of last week, we started talking about vector components, and on Friday, the day that I wasn't here, you learned a little bit about vector addition. The whole point of vector components wasn't so much an end in itself. The whole point of vector components was so that we could learn to add vectors together that were in 2 dimensions. Let me just review a couple of things from last week, and then we'll go check our worksheet that we did on Friday. If this is our XY axis, everything along the horizontal would be X, everything along the vertical would be Y. So if I have a vector that looks like this, that happens to be, let's say, 10 meters, we would say the X component of that is 10 meters, and the Y component is 0, because all of it is on the X-axis, and none of it is on the Y-axis. If we had a vector like this, that was 5 meters, we would say the Y component of this is 5, and the X component of this is 0. Y component is 5 because all of it is on the Y-axis, and the X component is 0 because none of it is on the X-axis. This one, actually, let's do it over here. Doesn't really matter where I do it. Okay, in the end, if this one is 8 meters, we would say the X component is -8, yeah? It's on the X-axis, but it's going to the left on the X-axis. So we would say the X component would be -8, and the Y component would be 0, right, because none of it is on the Y-axis. If we had something that looked like this, 5 meters pointing downward, the X component is 0, and the Y component is -5. Good. Now, what if we do one that looks like this? I've got a vector here that is 10 meters, and that's at an angle of 30 degrees. You see that I've got the XY axes drawn here. Those don't play any factor in finding the components here other than reminding us which is the X-axis, which is the Y-axis. So it helps us to remember X-axis, Y-axis, but we're not going to use that in actually determining how much of it is X and how much of it is Y. How do we figure out how much of that is X-axis and how much of it's Y-axis, Connie? Okay, first we need a triangle. So let's draw a triangle around it. Actually, usually I draw that in red, although it doesn't really matter. And then I draw my X component usually in blue. Again, it doesn't really matter what colors I use, though. And the Y component like this. My angle was 30 degrees, I think it was. So I've got my triangle drawn. We have to draw an X component and a Y component around the angle. I don't want to draw it up here, because that wouldn't be around the angle. Right? The angle has to be inside the triangle. So that's not the triangle that I want to draw. This is the triangle that I want to draw. Now, let's get rid of this because it's looking a little cluttered. Now I can find the X component and the Y component with a little bit of trick. You guys remember those trig functions that I reminded you of, refreshed your memory of last week? Cosine theta is equal to, sorry, we should go sine theta first, right? Sine theta is equal to, remember? SOHCAHTOA. Sine theta is equal to opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. And we said tan theta is equal to opposite over adjacent. SOHCAHTOA. Sine theta is opposite over adjacent, opposite over hypotenuse. Cosine theta is adjacent over hypotenuse, and tan theta is opposite over adjacent. If I'm looking for the x-axis here, which side of the triangle is the x-axis? Is that opposite, adjacent, or hypotenuse? It's adjacent, yeah? So I'm looking for adjacent. I've got that. Which side is the red side? Hypotenuse. I'm looking for adjacent. I've got the hypotenuse. I've got the angle. I'm going to use the cosine function here to find the x component. Cosine 30 degrees is equal to adjacent over hypotenuse. Rearrange that. X ends up being equal to 10 cosine 30, which is 8.6603 meters. Now the y component, we would say it's the opposite side of the triangle. We have the hypotenuse, so let's say sine 30 degrees is equal to opposite over hypotenuse. rearrange that, 10 goes up by multiplying, y is equal to 10 sine 30 degrees, or the y component is equal to 5.0 meters. So I've just solved for my x component, and I've just solved for my y component. It's very seldom that you get a question that is just that. You're not usually asked for the x component and the y component of a vector. That's more math class that you would be asked something like that, right? In physics class, this just becomes a tool to help us to add vectors together. We learned to add vectors together in late elementary, early junior high school, but vectors in one dimension. If I walk 10 meters to the east and 2 meters to the west, 10 plus negative 2 is 8 meters to the east. We can do that. We learned to do that several years ago. But we haven't learned to add vectors in 2 dimensions together until now. How do we add vectors together? If I was given this vector and some other vector, or 3 or 4 other vectors, well, we have to draw what's called a vector diagram. And a vector diagram is a diagram that shows all of the vectors drawn head to tail. If I draw a vector, this is the head of a vector, this is the tail of a vector. The vectors that I want to add together have to be drawn in a vector diagram, head to tail. So in other words, something that looks like this. If I was adding these 2 vectors together, that's a good vector diagram, because you can see that it's the head of one vector to the tail of the next vector. This would not be a good vector diagram, because that's drawn head to head. This would not be a good vector diagram, because that's drawn tail to tail. This would be a good vector diagram because, again, it's drawn head to tail. All the vectors that I want to add together must be drawn in a vector diagram head to tail. If there's 2, great. If there's 4, great. Okay, your vector diagram does not initially have to be a triangle, although the goal is to get a triangle. Ultimately, we need to get a triangle. In fact, a right angle triangle, so that we can do a little bit of trigonometry with it. But your initial vector diagram doesn't have to be a triangle. It can have 17 sides if there's 17 vectors that you're trying to add together. Got it? The resultant vector, which is the sum of all the vectors, it's the total. Right? If I was adding 10 plus 8, 10 east, 8 to the west, the total would be 10 plus negative 8 is 2 to the east. Okay, the 2 would be my resultant vector. The resultant vector, drawn in red here, is the sum of all the vectors. And it's the one that doesn't follow the same rule as all the other ones. All the other ones have to be drawn head to tail, head to tail, head to tail. The resultant vector, which is the sum of all the vectors, is drawn from start to finish, tail to tail, and head to head. So it's opposite to the rest of it. Does that kind of make some sense? All right. If I was adding together, let's say 10 meters to the east, and I wanted to add to that 3 meters to the south, how would I draw that vector diagram? Draw it on your page right now. Okay, draw it on your page right now. I want to add these 2 vectors together. Just draw the vector diagram on your page. Don't worry about solving it. Okay, I'm not concerned about that right now. I just want to make sure that you have the vector diagram drawn correctly. These 2 vectors drawn together, added together, such that they're drawn head to tail. The resultant vector, you should use either a different color for that, or a dotted line for that, or something to distinguish it. The resultant vector should be drawn from start to finish. All right, we've got 2 options for this. We'll see how many people drew which option here. The first option might look like this. We've got 10 meters to the east, and we've got 3 meters to the south. How many people drew it like this? Head to tail. The resultant vector should be drawn from start to finish. So strictly speaking, to have this perfectly correct, you should have your resultant vector drawn like this as the hypotenuse of this right angled triangle, and it's going to go from tail to tail, head to head. Anybody draw it differently? Anybody draw it like this? 3.0 meters to the south, 10 meters to the east. the resultant vector goes from start to finish. Anybody do that? Which one's correct? Both of them are. If you were adding vectors together in one dimension, let's say 10 meters to the east, 8 meters to the west, we would say 10 plus negative 8 is 2. Or we could say negative 8 plus 10 is 2. It didn't matter what order we added vectors in one dimension. It also doesn't matter what order we add vectors in two dimensions. This is 10 plus 3 is equal to something. This is 3 plus 10 is equal to the same something. How do we find that something? How do we find what that resultant vector is? That total, that sum of those 10 and 3s? Yep. Good. We're going to use the Pythagorean theorem because we have a right angle triangle. Now remember, not all vector diagrams give us a right angle triangle. These ones do. We can find R right away here by using the Pythagorean theorem. If we don't have a right angle triangle right away, we'll get one and then do exactly what Judith just said, which is use the Pythagorean theorem. So we're going to say for this R, Pythagorean theorem, if you don't remember, says a squared plus b squared is equal to c squared. C is the resultant vector, the hypotenuse. So C would be equal to the square root of a squared plus b squared. Or R is equal to the square root of 10 squared plus 3 squared. Let's figure out what that is on our calculator here. Let's say second function square root, use some brackets, 10 squared plus 3 squared gives me, and that bracket gives me, in scientific notation now, let's get rid of that. Gives me 10.4. Is that my resultant vector? That's the magnitude of the resultant vector. A vector has magnitude and direction. So we need a direction for this as well. The direction for this is theta, the angle. Now the angle, theta, is always drawn at the start of the vector diagram. You can see here that I've got it drawn at the very beginning where I started. Right here, theta drawn at the start of the vector diagram right here, theta drawn at the start of the vector diagram right here. Now, you can imagine that these two angles are going to be different values. That's why I've got them in different colors here. We'll explain the difference in those in just a moment. But let's figure out what they are right now. Let's figure out what the red theta is. Remember, there's three trig functions that we're concerned with. Sine is equal to opposite of hypotenuse. Cos is adjacent of hypotenuse. Tan is opposite over adjacent. You can see in both of these cases, but particularly for the red theta, that's what I'm doing right now, I've got the opposite and adjacent side of the triangle. I've also got the hypotenuse, but I solved for that. So let's try not to use that one in case I made a mistake on it. Let's use the ones that I was given, the 3 and the 10. I'm going to say tan theta is equal to opposite over adjacent, or tan theta is equal to 3 over 10. Now, to actually write that out, to solve for theta, I mean, that's correct. But to rearrange it to solve for theta, I would say theta is equal to the inverse tan, or second function tan, of opposite over adjacent. You can see that 3 is the opposite side because it's not touching the angle. 10 is the adjacent side. It is touching the angle. And it's not the hypotenuse, so it must be the adjacent. Okay, let's figure out what this is now. Let's first do a little trick on our calculator just to make sure we're in degree mode. We should do this every day that we're using angles. If we're doing an angle calculation in class, we should check to make sure we're in degree mode. Let's say sine 90. 1. All right. So I'm in degree mode. I'm good to go. Now, to find the inverse tan of 3 over 10, I'm going to say second function tan of 3 divided by 10. Gives me a value of 16.69, or we'll say 17 degrees. Now, if I was solving for the green theta, I would say it's the inverse tan of opposite over adjacent. The opposite side in the second diagram here is 10. The adjacent side is 3. Let's figure out what the inverse tan of 10 over 3 is. Lightning fast calculation in my head. I'm going to say 73 degrees. Let's figure this out. The inverse tan, just to make sure, the inverse tan of 10 divided by 3 is, look at that, 73 degrees. How did I get that so fast? Because I've got all the trig tables memorized in my head? No, because 90 minus 17 is 73. If I solve for this angle right here, the red angle, the green angle is the complement, and it's always 90 minus that. Now, how can they both be right? If I asked you what my position is right now, where am I? What's my position? Hey, Grant might say, I'm 1 meter from the front of the room. But Brad might say, I'm 7 meters from the back of the room. So Grant says, I'm 1 meter from the front. Brad says, I'm 7 meters from the back. Who's right? Both. 1 meter from the front, 7 meters from the back. Two completely different numbers, but two numbers that are both correct. The difference there is your reference point. Grant uses the front of the room, 1 meter from the front. Brad uses the back of the room, 7 meters from the back. Both correct, right? So both of these angles can be correct as well, as long as we have a reference point. We're going to say that this is 17 degrees south of east. Why south of east? Because the angle is measured from the east, right? It's touching the east axis. It's measured from the east, but yet it's going south from the east. South from east. 17 degrees south from the east, or south of east. This is going to be 73 degrees east of south. Here's my little XY coordinate at the start of the vector diagram, and you can see here that I'm measuring my angle from the south, but yet I'm going east from the south. So we're going to say that my angle is 73 degrees east from south, or east of south. Okay? 17 degrees south of east, 73 degrees east of south. That's like saying Grant says I'm 1 meter from the front of the room, and Brad says I'm 7 meters from the back of the room. Does that make sense? Which one's better? Well, which description of my position is better? 1 meter from the front, 7 meters from the back. Like, neither of them is better, right? Like, they're both correct. So both of these would be correct as well. Now, the hypotenuse is going to be the same any way you look at it, right? The resultant vector is 10.4 meters at 17 degrees south of east, or the resultant vector is 10.4 meters at 73 degrees east of south. Either one of those is okay. Got it? Okay, I'm going to put one on the board right now and just see what you guys can do at your desks for just a few minutes. I know that you guys had a worksheet to work on Friday, and I know that we haven't looked at that yet. We'll get to that, okay? I just want to make sure that you're in a spot where that worksheet makes enough sense that we can go over it, right? So let's put another one on the board right now. Let's say I've got a vector that is 8.00 meters to the south, and I've got another vector that is 4.00 meters to the west. Draw a vector diagram, including the resultant vector, with your arrows on it. Okay, don't just draw the sides of it, draw your arrows. And then find the resultant vector. In other words, add these vectors together. Let me give you a hint. If I say add these vectors together, the answer is not 12. If I said add them together as scalars, the answer would be 12. But add these vectors together, it's something else. We'll see what it is in just a moment here. Okay, let's have a look, guys. Keeping in mind that there's always more than one way to draw these diagrams, always, every single time. We want to add these vectors together. We can add them together like this, with 8.00 to the south, then 4.00 to the west. Is that good? Yeah, that's good. That's drawn head to tail, so that's okay. Now the resultant vector, which I'm going to draw in red, you might draw as a dotted line, whatever, is going from start to finish. Let's label that R, and let's label the angle as well. Where's the angle going to be? Position 1, 2, or 3? Somebody said position 3. Yes, the angle is going to be position 3. We know that because that's at the very start of my vector diagram. Now, there's another way to draw this as well. I'll draw that over here. I could have drawn it like this. 4.00 meters and 8.00 meters to the south. Is that okay? Yep. Those vectors are drawn head to tail. The resultant vector is drawn from start to finish right here. Where would I label my angle here? Position 1, 2, or 3? Position 2. Always drawn at the start of the vector diagram. Now, I can solve for r, and r is going to be the same value either way. It has to be. The magnitude of the resultant vector is always going to be the same regardless of which way you draw your vector diagram. I'm going to figure that out by the Pythagorean theorem. C is equal to the square root of a squared plus b squared, or r is equal to the square root of 4 squared plus 8 squared. Or you could have said the square root of 8 squared plus 4 squared would have been the same thing, right? Let's figure out what that is. Let's say second function, whoops, wrong button. Second function to get square root, second function x squared to get square root. Use some brackets, 4 squared plus 8 squared, end the square root, or end the bracket. I get a value of 8.94. Is that my answer? Final answer for the resultant vector? That's the magnitude of the resultant vector, but the resultant vector also includes a direction. Let's change the color of one of these actually. Color coded here. Let's make this one green. If I'm solving for the red angle right here, the red theta, we're going to say theta is equal to the inverse tan of opposite over adjacent. What's the opposite side of the triangle here? Cassie, what's the opposite side? 4 or 8? For this one here? 8. So the inverse tan of opposite, the other side is 4 adjacent. The inverse tan of 8 over 4, we'll say second function tan. I don't need to do sine 90 again on my calculator, right? I know I'm in degree mode. Unless I change it, I'm going to stay in degree mode for the whole class. We'll just check it once at the beginning of a problem, our first problem of the day. The inverse tan of 8 divided by 4 gives me 63.4 degrees. But we need a reference point, right? Am I 1 meter from the front of the room or 7 meters from the back of the room? Well, I'm going west and I'm going south. Is this going to be west of south or is this going to be south of west? Who said that? Okay, Nicole, you're right. It's going to be south of west. If you have trouble visualizing it, draw a little XY coordinate system there. And look, you can see that the angle is touching the west. It's not touching the south. It's touching the west. But yet I'm going south from the west. South from west. Or south of west. Now, the other way to express that angle, and either way is okay, you don't have to do it both ways, by the way, one way is fine, is the inverse tan of opposite over adjacent. That's going to be 4 over 8. Right over here in the second diagram, you can see the opposite side is 4, the adjacent side is 8. The inverse tan of 4 over 8, I know what that's going to be right now, 90 minus 63.4. It's going to be 26.6 degrees. But let's just figure it out just to make sure. The inverse tan of 4 over 8 gives me 26.6 degrees. Sure enough. This one is going to be, where am I measuring my angle from? The south or the west? What's it touching? South. Okay, but yet I'm going from the south, west from the south, west from south, or west of south. So we say it's 63.4 degrees south of west, or it's 26.6 degrees west of south. Good? Okay. I want to do one now that's a little trickier. This one is not going to be a triangle right off the top. We're going to get a triangle, Judy, so that we can do the Pythagorean theorem like you said for these, right? You told me to do the Pythagorean theorem? Absolutely, that's what we want to do. But we can't do that until we get a right angle triangle. So let's see one now where we don't have a right angle triangle right off the top. Let's try this. Let's say we've got 10 meters to the south. Let's say we've got 5.0 meters to the east. And let's say we've got 3.0 meters to the north. Let's add those together. Now, keep in mind, as I add these together, I can add them together whatever order I want. 10 plus 5 plus 3, 3 plus 5 plus 10, 10 plus 3 plus 5, it doesn't matter. I'll probably go in the order that they're given here, but it doesn't really matter any more than it matters what order I add. 10 plus minus 8 is 2, 10 or minus 8 plus 10 is 2. It doesn't matter what order. I'm going to go this way. 10, 5, and 3. Is that okay? Is that legit? Yes, it is. All of these vectors are drawn head to tail, head to tail. The resultant vector is going to be drawn from start to finish. Now, this is not a right angle triangle. We can't figure out what this is right now, but let's get one. Here's how we're going to get one. If we have more than two vectors and not a right angle triangle already, let's break it down into x components and y components. Each vector into x components and y components. What's the x component of that 10? We've done this, right? We did this last Thursday. We did this earlier during review. What's the x component of the 10? 0. What's the y component of the 10? 10? No, almost though. Somebody said it? Negative 10. Good. What's the x component of the 5? How much of that 5 is x component? All of it. 5.0 meters. How much of its y component? 0. All of its x. How much of that 3 is x component? 0. It's all on a y-axis, right? So we're going to say 0 and 3. Good. Now, let's add up the x's. 0 plus 5 plus 0 is 5. Negative 10 plus 3 is negative 7 meters. Good? Now I can get my right angle triangle. I'm going to redraw this now. I'm going to say 5 meters to the east, and I'm going to say 7 meters to the south. How did I know it was to the south? Because it was negative. The x component is plus 5, the y component is negative 7. The resultant vector will be drawn from start to finish. That resultant vector, if you draw this to scale, should look the same as this resultant vector, because it's the same thing, except that we've simplified it and turned it into a right angle triangle. Now it's easy, right? We know what to do for this. Let's solve for r, and let's solve for theta. Where do I put theta? Position 1, 2, or 3? 1, 2, 3. Position 1, at the start of the vector diagram. We're going to say r is equal to the square root of 5 squared plus 7 squared. Second function, bracket, 5 squared plus 7 squared, and the bracket, 8.6 meters. And we're going to say theta is equal to the inverse tan function of opposite over adjacent. The opposite side is 5 or 7. Theta to the opposite side, 5 or 7. 7. Good. So it's going to be the inverse tan of 7 over 5, which on my calculator, on my calculator it says it is 54 degrees. 54 degrees of what? Of what? I'm going east and I'm going south, right? Is it east of south or is it south of east? What is it? South of east, yeah. Because I'm measuring my angle from the east. It's touching the east, but yet it's going south from the east. So we'll say it's 54 degrees south of east. Now, if you had have drawn this, I'm not going to do it the other way this time, but if you had have drawn it the other way, the 7 and the 5, you would have still gotten 8.6 meters, but you would have got an angle of 36 degrees east of south. Anybody get that? 36 east of south? Equally is correct, right? I would mark both of them correct. 100%. Good? So what's different about this question than the last one we did? Well, what's different about it is that we didn't start with this right angle triangle. We needed to get a right angle triangle. And we got the right angle triangle by doing the x and the y components. You got that? So you can imagine how now if I had a vector diagram with 37 vectors, which you're not going to get that, of course, right? But if I had one with 37 vectors rather than 3, I could do this. I just have to do the x and y components 37 times rather than 3 times. Cassie? Yeah, that's a good question. The question was, do we have to draw the initial vector diagram, or can we just go straight from over here to here? Technically you could, but you shouldn't. You should draw that vector diagram. The reason is, you can take a look at the resultant vector that I see right here, and the resultant vector that I see right here. And I haven't drawn it perfectly to scale, so they're not exactly the same. But you can see that, okay, it's probably right because they're pretty close to the same. Right? You're not going to have that little check if you don't draw that initial vector diagram. Okay? We're not concerned, at least we shouldn't be concerned, about investing 30 seconds of our life in doing a little bit of extra work if it's helpful, right? If it's not helpful, don't do it, right? But if it's helpful, let's spend a little bit of extra time. This doesn't take long, and it is helpful because, again, we can see that the resultant should go down like this. If I had it drawn, my second one, my triangle here, and my resultant vector went down like this, clearly I made a mistake somewhere, right? So I'd have to go back and check my work, but at least I'd know it. Okay, let me draw one on the board for you. You guys try this one. Let's say we've got 10 meters to the west. Let's say we've got 5 meters to the north. Let's say we've got 5 meters to the west. And let's say we've got 15 meters to the south. Now you could technically draw this any order you want. I'm going to suggest that you draw it in the order that they're given here, right? See what you can do on that, and then we'll take a look at it in a couple minutes. All right, let's draw this in the order that we have them, although, again, we can draw them whatever order we want. What we can't do is draw it like this. Here's 10 meters. Here's 5 meters. Well, I can draw it like that. I can't draw it like this, or at least the first two. Why can't I draw them like that? Head to head. Can't draw it head to head. So we're going to say 10 meters, 5 meters. Let's go another 5 meters over here. And let's go 15 meters down. Is that good? Now that's not drawn to a perfect scale. The better the scale, the easier it is to see if you've done it right, because your proportions would be correct, right? And we're going to get rid of these just to declutter a little bit. Draw my resultant vector, goes from start to finish, so it looks like this. Now my angle is going to be right. I'm not even going to draw my angle right now. Just label R. Good? Now this is not a right angle triangle. The goal is to get a right angle triangle. So let's do that now. Let's get a right angle triangle. We're going to do that by doing x components and y components. What's the x component of the 10? The first one. Quick, what is it? Negative 10. What's the y component of that 10? 0. What's the x component? Jacob, what's the x component of that first 5? 5. Sorry, no it isn't. 0, right, good. What's the y component? Good. What's the x component of the next 5, Cassie? Of this one here? Yeah. Yeah, we're going to make it negative though because it's going to the left. And the y component would be good. And what's the x component going to the 15? 0. And the y component is negative 15. Good. So let's add these up. 10 plus negative 5, negative 10 plus negative 5 is negative 15. 5 plus negative 15 is negative 10. All right, now I can get a right angle triangle. I'm going to do that by drawing 15 over to the left. How did I know to draw that to the left, not to the right? Because it's negative. Okay, now I got 10 meters to the south, so I'm going to draw that down like this. How did I know to draw that down as opposed to? Good, because it's a negative. The resultant vector is drawn from start to finish, and you can see that resultant vector doesn't look exactly like the first one because I haven't drawn it to a perfect scale, but it's close, which tells me that I've probably done it correct. Let's find the value of r now. It's the square root of 10 squared plus 15 squared, or 15 squared plus 10 squared, doesn't matter. Second function, x squared bracket 10 squared plus 15 squared. Gives me 18. And theta is the inverse tan of opposite over adjacent. What's the opposite side here? Is it 10 or is it 15? The opposite side of the triangle. What is it? The opposite side is 10, so we're going to say the inverse tan of 10 over 15, which is, second function tan 10 over 15, gives me 34 degrees. That would be 34 degrees what of what? Where am I measuring it from? Okay, I didn't even label that, right? I should have labeled it right there. It would be south of west because you're measuring the angle from the west, but you're going south from the west, or south of west. 34 degrees south of west. So, if the question says, add these vectors together, the answer is 18 meters at 34 degrees south of west. If the question says, find the sum of the vectors, the answer is 18 meters at 34 degrees south of west. If the question says, find the total of all these vectors, the answer is 18 meters at 34 degrees south of west. There is one more answer that you could give that would be correct. If you had have drawn this diagram differently, you had have drawn the 10 and the 15, you would have gotten 18 meters at, anybody want to take a stab at this? 18 meters at 56 degrees west of south would also be correct. So you're not going to get that from this diagram, but if you drew this diagram differently, like this, you would have gotten 56 degrees west of south. Is that good? Got it? How about this one? Let's see what you can do with this one. This is 10 meters. This is 10 meters at 30 degrees north of east. Let's find the sum of these vectors. I'll do this one with you, okay? Let's draw it first. 10 meters. And then the next one would be 10 meters at 30 degrees north of east. The resultant vector would be right here. That's a triangle. I can do the Pythagorean theorem, right? No, it's not a right angle triangle. So I can't do the Pythagorean theorem here. What's the goal? I got to get a right angle triangle. So how are we going to get a right angle triangle? The same way as we just did. Do the x components, do the y components. The only problem is the x and y components of that second vector a little bit more challenging. So here's what I want to do. I probably would have said this in the podcast that you saw on Friday when I wasn't here. I want you, when you see an angle like this, it's 30 degrees or any degrees except for 90, I want you to repeat in your head 5 words. I, say it aloud, and that's this time though. I don't like funny angles. 30 degrees is a funny angle. 64 degrees is a funny angle. 89 degrees is a funny angle. 90 is not. I'm okay with 90s. I don't like funny angles though. I don't like 89 degrees. I don't like 30 degrees. I don't like 16 degrees. I don't like anything other than 90. So what do we want to do? We want to get rid of it. We don't want the 30 degrees here. Let's get rid of it. We know how to get rid of it. We've gone through that, right? Thursday, Friday, and earlier today. Let's take that one vector we have that's 10 meters at 30 degrees, just bring it off to the side over here. Do you see what I did there? I just took the one vector and took it off to the side. And then let's do what we did earlier. This is x, and this is y. The x component of this triangle, remember we're not solving for the final answer here. Remember earlier today I said when you were finding the x component and y components of vectors, it was just kind of a tool to help you figure out a bigger problem? This is the bigger problem. Let's figure out the components of that vector. Let's say cosine 30 degrees is equal to adjacent over hypotenuse. And let's say sine 30 degrees is equal to opposite over hypotenuse. You guys see what I did there? I haven't done anything with this yet, right? Nothing with this. All I did is took that one vector that I didn't like because it was at a funny angle and found the components of it. You'll see the value of that in just a moment. Now, what am I going to do with those components? Here's what I want to do with them. Let's erase this 10 meters at 30 degrees right here. Let's get rid of it. 10 meters, 30 degrees. It's gone. It's gone forever, out of my life. Forever. It's not 10 meters at 30 degrees anymore. It's 8.6603 meters and 5 meters. See what I did? You see what I did there? I don't like that 10 meters at 30 degrees, so I got rid of it. And I turned it into an 8.66 and a 5. I'm okay with those because those are at 90 degrees, not a funny angle. Now you know what to do with this, right? We just did a couple problems like this. Now you just go x components and y components. The x component of the first vector is 0. The y component is neg 10. The x component of the second one is 8.6603 and 0. The third one is 0 and plus 5. We add these up. Now let's redraw it. 8.6603 and 5 down. We know that it's down because it's negative. And we draw a resultant. Oh, look what we get. Isn't that pretty much like we just got in the original? This is going to be r. This is going to be theta. Now let's figure out what r is, and let's figure out what theta is. R is the square root of 8.6603. Whoops. Squared plus 5 squared. So r is going to be, let's figure that out here, second function squared, bracket 8.66 squared plus 5 squared gives me a value of 10. Look at that. Almost exactly 10. We'll say 10 meters. And theta would be the inverse tan of opposite over adjacent. What's the opposite side? Is it 8 or is it 5? 5, yeah. The inverse tan of 5 over 8.6603. 30 degrees. Look at that. That would be 30 degrees south of west, because I'm measuring the angle from the west, but yet I'm going south from the west. So add all of these vectors together. Well, there's only two, I guess. 10 meters to the south, and then 10 meters at 30 degrees north of east. The sum of those vectors is, funny enough, 10 meters. 10 plus 10 is 10 at 30 degrees south of west. So that should be south of, not west. South of east, yes. Because east is to the right.